great to see so many people constantly coming in. We know that for some of you it's the middle of the night, but for many of us it's a busy time in the year. So we're really grateful for all of you for having somehow made the time to join us today. Nick, if I could have the next slide. This talk, of course, is about the manifold hypothesis. So this is an idea which it's fair to say perhaps really took hold in the 21st century. So the idea is possibly quite nicely described in this quote by Lawrence Caton, who described the manifold hypothesis as this idea that the dimensionality of many data sets is only artificially high. So although each data point consists of perhaps thousands of features, it may be described as a function of only a few underlying parameters. That is, the data points are actually samples from a low-dimensional manifold that is embedded in a high-dimensional space. So this hypothesis has had implications for a wide range of statistical endeavors. So, of course, to start, there's everything to do with dimension reduction and visualization. So in the early days, that was things like PCA. But from the beginning of the 21st century, quite a lot of nonlinear dimension reduction techniques started being proposed. And in the early 2000s, for example, there was isomap, and more recently, methods like t-SNE and UMAP have become very popular, and there are many others. Manifold estimation is, of course, predicated on the manifold hypothesis, and so is topological data analysis, which is a connected field. And finally, it's probably worth mentioning that the manifold hypothesis is often held as an explanation for the empirical performance and success of AI. So there are many papers, and some of the authors of those are here today, that have studied neural networks and shown that they can somehow adapt to manifold structure. So, for example, they might find that the learning rate is a function just of a manifold dimension, and not the data dimension, and that could represent potentially quite a huge improvement. So next slide, Nick, please. To understand the nature and the potential value of our contribution, we thought it would be a good idea to start with some scientific applications. So the first example that we're going to look at is relates to the brain and how it models physical space. So the authors of this paper, the lead authors of this paper, Moser and Moser, they won the Nobel Prize for identifying the system of the brain responsible for this mapping of physical space. And in this paper, they managed to isolate the relevant neurons, these grid cells. They get 150 of them, and they monitor the activity of those cells in a rat as it moves around space. So the analysis they do here, which is quite typical, is they take this 150-dimensional time series, they apply PCA to reduce from 149 down to 6 dimensions, and then they apply UMAP, a nonlinear dimension reduction technique, to go down from 6 to 3 to get the picture that you see here. So it's important to realize that the scientific objective here is to somehow understand how physical space is getting transformed into some sort of structure which is embedded in high-dimensional space. And indeed, in this paper, they were able to validate a long-standing hypothesis that this structure is, in fact, a torus. Next slide, please, Nick. So the second example I want to show you is it relates to stem cells, right? So stem cells, as you probably know, are cells that are known to evolve and then differentiate until they become more specific cell types. So the authors of this paper, which was published in Science in 2018, managed to get hold of many stem cells belonging to an organism called the planarian, and conducted single-cell transcriptomics to get gene expression data for every cell, resulting basically in something like 6,000 dimensional representations per cell. So what they did in this paper is a very similar workflow. They take this 6,000 dimensional data, they apply PCA this time down to 14 dimensions, and And then t-SNE, so another nonlinear dimension reduction tool, to go from 14 down to 2 dimensions. And that's a plot you see on the right. So the colors here represent known cell types. So these are cell types that have been inferred in existing studies. And again, the scientific objective here, it should be appreciated is one of trying to map an underlying biological mechanism. Specifically, I have a bit of an echo or something going on. But anyway, underlying a biological mechanism, specifically the process of differentiation of stem cells, and to understand how that maps into a structure which is embedded in high-dimensional space. And in this paper, the authors were able to establish that that structure looked very much like a tree, which looked very much to represent the lineage of the stem cells. So next slide, please, Nick. Okay, so looking more broadly, this style of exploratory data analysis based on the manifold hypothesis. So this workflow, for example, of doing PCA and then UMAP and then some sort of coloring based on explanatory variables, it's hugely popular. And in fact, it will often constitute the only type of statistical analysis in a paper. Right, so just to exemplify a little bit the popularity of this sort of methodology, I mean, the t-SNE and UMAP together have something like 80,000 citations. So the widespread popularity and the widespread impact of this sort of approach, we think means that statisticians should try to get a better understanding of this workflow. And that really is the primary goal of this paper. Next slide, Nick. Okay, so looking in a slightly more detail at the examples you just saw, I think these are questions that you would have had yourself when you saw the examples, right? The first one is PCA and tools like t-SNE or UMAP are often presented as alternatives, but actually we see that in practice. It's very often the case that they're used together. So what people will often do is PCA into some sort of moderate dimension and then say UMAP into low dimension. And so one question you might have is why? Why is it helpful or productive somehow to do PCA first? The second point I want to make is, of course, it's quite well understood now, right, that t-SNE and UMAP figures can be a little bit misleading. And I'll point you there to a few high-profile controversies in the literature. But that leaves the question, what should you do instead? Right? Should you be doing analysis of a raw data, or should you be using a PCA embedding? And the final question I want to put to you is, it was obvious in those scientific applications, right? But the question wasn't just somehow estimating the manifold, but rather understanding the relationship between the manifold and some sort of real-world explanation, such as spatial location or phylogeny. Next slide, please, Nick. So to summarize our main contributions, in this paper, first we propose a model and some associated theory. And this model, first of all, it explains how potentially quite complex hidden manifold structure might emerge from actually very simple statistical assumptions, so things like latent variables, correlation, stationarity. Our second result shows that a strong asymptotic sense in which PCA is able to somehow remove almost all the noise from the data. And this would strongly validate current exploratory data analysis practice of first applying PCA. And the second thing that and the third thing we do is we highlight different sorts of relationships through our model that could exist between the manifold and the ground truth, or some sort of explanatory variable which we think might be connected to the ground truth or reflect the ground truth. Over to you, Nick.
Thanks, Patrick. So about this model. It's a model for a data matrix Y, which has n rows and p columns, comprising 3 independent sources of randomness. There's a collection of n latent variables, denoted by z's, and they're drawn in an IID manner from some distribution supported on a metric space. So z is a set, and d is a distance function. And the second source of randomness is a collection of random functions, x1 to xp. The domain of each of those functions is z. And the third ingredient is a collection of noise variables collected in a matrix E, each of which is zero mean univariance random variables. And to add a bit of mathematical structure to the model to allow us to make some theoretical progress, going to assume, and throughout the rest of the talk, that Z is compact, that each of the random functions is mean square continuous with respect to the distance on the metric space, and that the elements of the noise matrix E are uncorrelated across I and independent across J. So two comments are in order about this model. The first is that it's intentionally generic. So we're not trying to write down a model which we think is really accurate for neuroscience data or for single cell data, or whatever. We're trying to write down a model which is intentionally generic and which we're going to consider as a data generating mechanism under which to understand the properties of PCA and other downstream techniques. And secondly, as will be apparent, there's no explicit definition or construction of a manifold in this model. But nevertheless, we'll see that in a certain sense that a manifold structure emerges from it. And a key object which allows us to move towards that is to introduce this kernel F. So that's a symmetric positive definite function, which we're taking to be defined implicitly in terms of the random functions in the model. And Mercer's theorem tells us that there is a vector valued function, here denoted by phi, which allows kernel evaluation to be interpreted as taking inner products. And I should say that we're not assuming any particular functional form for the kernel, but even if we did, in general, phi is not something that's available in closed form. Okay, Mercer's theorem tells us it exists, but it's not there in closed form. And it's a property of the model that I've shown you that the conditional expected squared distances between data vectors, given the latent variables, are given by the squared distances between the feature mapped latent variables up to some distortion depending on the noise level sigma. That's written there. And there are many existing works which have influenced the direction we're going in here, but in particular, we wanted to highlight this 2005 JRSSB paper of Peter Hall and co-authors, who introduced a way of thinking about the high dimensional behavior of distances between data vectors. We're doing something loosely related here, but in a different and in some ways more complicated modeling setup. All right. So the message here is that at least in this conditional expected sense, the shape of the point cloud of data vectors is strongly influenced by the corresponding point cloud of feature mapped latent variables, which is a collection of IID points in the set we're calling M here. That's the image of Z through the feature map phi. Okay. And under the condition that's shown here, that mapping phi, vector value mapping phi, is a homeomorphism between Z and M. So what does that mean? Well, homeomorphism is a function which is continuous, invertible on its image, and with a continuous inverse. And when thinking about homeomorphism between subsets of Euclidean space, well, informally speaking, we can think of mappings which involve deformation by stretching or bending, but not tearing or puncturing. And there's a stereotypical example of such a homeomorphic relationship is that between a cup with a handle and a donut with a hole in it, shown here. Because if the cup were made out of a malleable material, clay, Play-Doh, whatever, then it could be molded into the donut just by bending and stretching and compressing, but without tearing or puncturing. And in the setting of our model, we're going to consider M to be a manifold in the sense that it, at least under this condition, it has the property here of being homeomorphic to the latent space Z. So here's a sketch which just gives a very loose visual interpretation of what's happening in the model. We've got the latent space Z on the right-hand side, points in that getting mapped through phi up to this set M, which is a subset of a little L2, a vector space. And at least in the conditional expected sense that I showed earlier, then the geometry of the point cloud of the data is influenced by the shape of the point cloud of the feature map latent variables. And in the paper, we go on to consider other more expressive or rigid relationships between homeomorphism, but we don't have time to get into all the details of those today. So what I'm going to move along to is then the question of what role does PCA play in this situation? So to be clear, notationally, when we say PCA, what we're talking about here, we're talking about the result of applying PCA for dimension reduction, what people do in practice. The results in quantities which are often called the principal component scores. Okay, so that's that's dimension reduction down from P, which is the ambient dimension of the data, down to some lower dimension R, which is obtained by taking the inner products between the data vectors, the yi's, and the top R orthonormal eigenvectors of the sample covariance matrix. In this case, we're considering it to be uncentered. And under our model in the paper, then this is what we've been able to say about the behavior of PCA. So we say that Y is distributed according to the model I've told you a little bit about already, with the assumptions that I've shown you already. And additionally, the following: that the random functions in the model, x1, x2, and so on, are mutually independent. And secondly, that we consider the moments of the random functions and the noise variables to be uniformly controlled in the senses shown here, that the kernel F has a finite rank R, and with its positive eigenvalues, which are well behaved in a particular sense. So just to give a little bit of, a little bit of insight into the veracity of that assumption about the independence, might be worth bearing in mind that there's nothing in the model which requires our random functions to be random in a non-degenerate way. And we haven't assumed them to be identically distributed, and we haven't assumed that they've got mean zero. Right? So in particular, if x1 is with probability 1 equal to some deterministic continuous function, and x2 is with probability 1 equal to some other continuous function, then that assumption of mutual independence is automatically satisfied. I think the moment assumption kind of speaks for itself. What about this assumption on the kernel F? Well, very, very loosely speaking, the rank R of the kernel can be regarded as a measure of the functional complexity of the X functions. And what we have is that then if we apply PCA in the sense that I've shown you a moment ago to the data matrix Y to reduce down to the dimension R, the same as the rank of the kernel, then we find that as n increases and at the same time as P on n increases, that the vector of PC scores, that's the zeta variables, up to some distance preserving orthogonal transformation Q and some rescaling by P, they approach the feature map latent variables. So you'll recall that in the model, there were 3 independent sources of randomness: the latent variables, the random functions, the additive noise. And so what this is telling us is that in this particular asymptotic regime, under these assumptions, that the PCA effects, the effect of PCA is to expunge the randomness from the random functions and from the additive noise. So here's a little visual example just to try and convey what that result tells us. So it's a simple example where the latent space is a circle, and we've chosen the random functions to be Gaussian processes with a particular kernel. We've done that for convenience here, so that we know what the feature map phi is. We can write it down, and we know that R is 3 in this case. And across the subfigures from A to B to C, you're looking at the first 3 dimensions of the PCA embedding. And what you can see is that as the ambient dimension P increases, that point cloud starts to more and more strongly resemble the set M that we're regarding as a manifold. You see it resembles the underlying latent space subject to a deformation in the form of twisting and bending. Okay, and in this case, because R is 3, that set M lives in a 3-dimensional subspace. So how does this relate to what's been done before, the theory, the high-dimensional theory of PCA? Well, in the early 2000s, there was a flurry of work studying the asymptotic behavior of the eigenvectors of the sample covariance matrix and the question of consistency in the sense of how close they are to their population counterparts. And in particular, there's famous inconsistency results that, at least under a certain model and under certain assumptions, that if n does not grow faster than p, then those sample covariance eigenvectors are in fact inconsistent in a particular sense. But around the same time, and slightly later, as was published, the questions were asked about the fact that those very mathematically detailed consistency and inconsistency results didn't seem to have a bearing on whether or not PCA was useful for dimension reduction and visualization in practice, okay, which turns out to be a slightly different, crucially different question. And the spirit of our work, we think, is very similar in a way to the spirit of the 2 papers at the bottom of the slide here, which we're trying to understand the mathematical underpinnings of why PCA as a dimension reduction tool is useful for data exploration and visualization. And I don't have time to get into all the details, but just in short, what are we doing that's different from them? It's a different model, different assumptions, different estimand, and to some extent, different mathematical techniques as well. And Patrick's going to tell you a little bit about those now.
Great, thanks, Nick. So I'm just going to hop in quite briefly, really, before giving over to Annie. Just a line of work on graph spectral embedding, which has turned out to be completely crucial for our results. So it might seem perhaps like a bit of a strange connection, but the key identity is what you see here. It's YV, so that's what Nick introduced as the PCA embedding, and that turns out to be identically equal to the product of 2 other matrices, which arise as the eigendecomposition of the matrix of inner products between the data vectors. So it's a simple linear algebraic identity, but the point of it is that the right-hand side looks a lot like what is being constructed explicitly in something like adjacency spectral embedding. So that's a particular technique that was put forward by Dan Sussman and co-authors in 2012 in JASA. And since that paper, there's been this hugely successful research program mostly led by Carrie Priebe and his collaborators, where they made phenomenal progress on generally getting control and finer control on the entry-wise error of these embeddings. In particular, there's this paper by Vince Lisinski, which I fancy might be quite sort of easy to miss because they didn't necessarily make such a big deal out of it. But it has a theorem 5 in that paper, which it really looks a lot like our theorem in some ways. So, for example, the 2 to infinity subscript here refers to the maximum norm. This theorem also has an orthogonal matrix W, which also plays a role in our result. And we should be forthcoming in saying that we actually really borrowed almost all of the algebraic decompositions that were in that paper and just followed that analysis very carefully, just in a completely different context. So after that work, there were very many really interesting papers. A paper by the seminal paper by Joshua Cape and co-authors in the Annals in 2019. There was a really beautiful paper written by Mariana Pensky in last year, which sort of collected all these existing results in a new and interesting way. I just saw very recently that Min and Joshua, so Tang and Cape, have finally managed to address the infinite rank case, so that's very exciting, and there are many other papers. Next slide, please, Nick. Okay, so moving a little away from the theory now and going back to applications, I'd like to suggest to you that what is perhaps useful and scientifically interesting about the pictures that you see in all of these scientific domains is the element of comparison, right, between the geometry of a point cloud and the geometry associated with some sort of explanatory variable. So if you look at the middle figure here, for example, what do you see? I mean, you see a point cloud, but also the colors sort of tell you that the clusters are somehow meaningful, right? And there's more than colors, right? If you look at the actual labels, you see that in the top left, for example, you've mostly got countries in Asia. If you look at the bottom, you've got countries mostly in Europe. And we think that that combination of geometry of point cloud compared with the geometry of some sort of explanatory variable is what makes those examples exciting. So next slide, please, Nick. So given that what we think is the very standard scientific context of having both high-dimensional data and some set of explanatory variables, we just have a few modest suggestions for exploratory analysis, and then they don't involve tearing up the whole workflow. They really are just further possibilities that are perhaps inspired by a model. So perhaps the goal here could be to start thinking about exploratory data analysis in these contexts, but beyond visual inspection. In particular, are there quantitative ways of comparing topological or geometric shapes seen in the data point cloud to some known explanatory variables which we might think could represent the latent domain? So what does our theory kind of suggest to do? Well, the first point is it could be a really good idea to work at the level of PCA, right, rather than t-SNE or the raw data. It's possible that t-SNE is achieving, it's possible that PCA is achieving a very nice balance, a very good balance between the noise reduction that you get relative to using the raw data and the distortion that you might start incurring if you use things like t-SNE and UMAP. So it could be that PCA is a good sort of trade-off. Then point B is, our model would suggest really that long-range ambient straight-line distances are probably not very meaningful, or certainly not going to convey the latent distances, at least under our model. It tends to be a good idea to think more locally. So, for example, using notions of neighborhood. And finally, as Nick alluded to already and demonstrated already, we'd like to suggest at least 2 ways of thinking formally about the relationship between the manifold and these explanatory variables that you might have access to. So Nick mentioned one thing you could explore is a possibility that the relationship is a homeomorphism. And we have additional results in the paper that require slightly stronger assumptions, but are still quite mild, only things like stationarity, which would invite you to consider the possibility that the relationship is isometric. So what that means in big terms is that a path on the manifold has a length which might be proportional to the same path or the corresponding path on the metric space. So I'm going to pass over to Annie now.
Thank you. So the question remains how in practice we can actually explore this relationship between phi and our explanatory variables. In other words, what we want to do is understand the shape of our data in order to be able to compare it to some explanatory variables that we have. To do this, what we want to do is explore the topological and geometric features of our data, in particular those of the PCA embedding. And to do that, there are a number of well-known tools that are used to approximate manifolds. So we could utilize, for example, techniques from TDA, such as persistent homology, which can be used to detect topological features such as connected components or loops, or more generally, k-dimensional holes in data. Or to approximate a manifold, we can use k-nearest neighbor graph. So this is quite a standard procedure for approximating manifolds and appears often in the literature. For example, in ISOMAP, and both UMAP and t-SNE involve some kind of approximation with a nearest neighbor graph. So the figure on the slide is just a sketch to show how the k-nearest neighbor graph can be used to approximate shortest paths. So that's the distance along the manifold. So while these techniques aren't new, the novelty here lies in the interpretation of them in relation to the explanatory variables, for example, in some comparison of shortest path lengths. The exact techniques that one would use or the comparisons made would likely depend on the explanatory variables and domain-specific questions about the underlying data generating mechanism. Next slide, please. So to show this, we're going to go back to the stem cell example from the beginning that Patrick introduced. So just a quick reminder that the data here is gene expression levels of different cells, and the aim of this work is to discover the lineage tree which maps biological differentiation from stem cells to specialized cells. And then here, the explanatory variables that we have are known cell types. So within this example, we had broadly two aims. The first one, informally, is to investigate whether the data even has tree structure. So more formally, whether the latent variables are a continuous tree, which I've defined at the bottom of the slide, and phi is a homeomorphism. Secondly, we wanted to understand the relationships between the cell types, in particular, which cell types were close to each other in the PCA embedding. So more formally, whether Z is a lineage tree and the latent variables are the known cell types. So what's kind of important here is that the first point only considers the context or domain knowledge, whereas the second incorporates explanatory variables, allowing us to do some comparison between phi and the latent domain. Next slide, please. So for the first question, we tried to understand the shape of the PCA embedding, and we did this by comparing it to a baseline random embedding. And while there isn't time to go through everything now, we performed quantitative analysis using things like inner products and shortest path lengths of the k-nearest neighbor graph to understand how tree-like it is. But full details on that are found in the paper. Next slide, please. So finally, we explored the second question, and to do this, we did the following. So the left-hand side shows a visualization of the minimum spanning tree, which is derived from the k-nearest neighbor graph. So to get it, you remove edges from the k-nearest neighbor graph until a tree is formed. And this is done in a way that keeps the total edge length of the tree minimal. Here we incorporate the explanatory variables into the analysis by colouring the vertices by the known cell types. And it's quite clear on that plot that the cells of the same type are localised to branches in the tree, and similar types, such as all of the types of muscle cells, for example, will appear close to each other. And then to explore this further, we constructed what we called a class graph, which is on the right-hand side. And so this captures the relationship between different cell types implied by the minimum spanning tree on the left-hand side. So in this graph, each vertex corresponds to like a single cell type, and the undirected edge weight between any two vertices is defined to be the total number of edges in the minimum spanning tree between cells of those two types. And the size of each of the nodes here represents the total number of cells of that type, and the thickness of the lines represents the weights. So overall from this analysis, we recover a lineage using only the PCA embedding and known cell types, which closely aligns with the lineage found by Plass and co-authors, including those connections that were found through marker analysis. So back to Nick.
Thanks, Annie. So, that's what Annie's talked about is just one example of how to try and use the model to inform the structure of exploratory data analysis in a way which is somewhat different from what people might typically do when they use t-SNE or UMAP to reduce all the way down to 2 or 3 dimensions. More generally, from a methodological point of view, our aim in this work was to understand very popular exploratory data analysis techniques and combinations or variations of those techniques, which are simple enough to remain relevant to what data scientists actually do in practice. Of course, one can quite naturally ask about other methodological consequences of what we've done. And I think there's a number of directions in which this work could be taken forward, but I'll highlight just a couple. So on the topic of exploratory data analysis, well, clustering is an extremely important task in that domain, but one which we haven't really talked about in the paper, and we haven't talked about today. And in work which was initiated, in fact, after this manifold work started, but which ended up being published first, we've used a variant of the model I've told you about to derive a new approach to hierarchical clustering, in which similarity amongst data is quantified by dot products and understood as high dimensional behavior. And so that's certainly not the be-all and end-all of what can be said about clustering from this kind of perspective, but it's just one example. Beyond exploratory analysis, what can be said? Onto confirmatory analysis. What about model-based inference? Well, the model we've described is intentionally generic, right? Because if you remember, we wanted it to represent a general form of data generating mechanism under which to understand the behavior of PCA, etc. But in that form, I think we think it's in some ways it's too general to be useful for inference. Right? For inference, we'd need to make more specific statistical assumptions. So if the latent space in our model is Euclidean, and the random functions are IID zero mean Gaussian processes, and the noise variables are also Gaussian, well, it turns out our model reduces to what Neil Lawrence introduced under the name of a Gaussian process latent variable model. And in that setting, because of the Gaussianity and the structure of the model, it's possible to integrate out analytically the random functions and the noise, and you obtain a closed form likelihood function for the latent variables. And moreover, in that setting, the user has to make a choice for what that kernel is, the kernel that I showed you earlier. Okay. And I think in light of our theory, I think it starts to become clear that whatever choice of kernel is made can translate into extremely specific assumptions about the sort of limiting high dimensional geometry of the data under that model. And that might go some way in explaining why such a model can fit badly in practice. So a little more broadly, I think we think it's worth revisiting that Gaussian process latent variable methodology to take that into account. Another way in which the model could be altered or developed is not only through making more specific statistical assumptions, but by tailoring its structure in the ensuing analysis to specific domains of application or scientific questions. And again, we've tried to be somewhat general in what we've done, but there's lots of room, we think, and probably lots of utility to be obtained by being, in fact, much more specific. On the theory side, well, as Patrick described, we've kind of ported some mathematical ideas over from some of the literature on spectral embedding of graphs. But at the level of the behind-the-scenes mathematics, we've done that in really quite a heavy-handed way, just to sort of suit our aims. And we think it's very likely that the theoretical aspects of the work could be refined and extended by those who are more knowledgeable, more skilled than us in statistical theory. So questions about this assumption about dependence across dimensions, that's something we've made in order to be able to invoke a particular matrix inequality. To what extent can that be relaxed? What happens when a kernel is infinite rank? What happens if we consider the random variables to be sub-Gaussian, and so on and so forth? All interesting questions. But whatever is developed in terms of creative methodology or refined mathematical theory, the big challenge is to transfer whatever that expert statistical knowledge is into the heads, into the hands of people who might make use of it. And we all know, that's not an easy thing to do. But putting aside the details of manifolds and similarly abstract and sophisticated things for a moment, we hope that our work conveys a message that an important first step towards transferring that knowledge is to pay attention to what data science actually do in practice, what's popular in practice, what works in practice, and not just what we as statisticians think that they should do. And on that note, we'd like to thank you all very much for listening.
An interesting presentation, and now I would move on the discussion. I would like to call on Tengyao Wang from London School of Economics to propose the vote of thanks, which hopefully is here. Yes, I can see him. Good.
Sorry, I forgot to unmute myself. Okay. It's a great pleasure to propose a vote of thanks to the authors for the fascinating paper, which offers a new perspective on one of the central ideas in modern data science, the manifold hypothesis. So the manifold hypothesis, as the authors have mentioned, is a belief that although our data often live in this high-dimensional ambient space, there are meaningful variations typically occur in a much lower dimensional manifold. And this is the reason that statistical data analysis is still possible in the high-dimensional space and can survive the curse of dimensionality. So what is striking about this paper, I think, is that instead of assuming that there's this manifold hypothesis, the authors try to explain why such low-dimensional structure can arise in a natural way using a kind of as a consequence of statistical dependencies between random features, using a model they call the Latent Metric Model. And in this sense, we can view the Latent Metric Model as a probabilistic justification of the manifold hypothesis. And I think the authors have already done a very good job explaining why the Latent Metric Model works. And maybe let me just very briefly summarize my understanding of it so that I can kind of use it for the discussion later on. So the model starts with P-centered random functions, random coordinate functions, x1 up to xp, and then they're defined over some latent space curly z here. And then the observations are just these random functions evaluated at some latent positions zi's in the space plus some perturbations, right? And the important quantity that the authors used is the mean correlation kernel. So the mean correlation kernel here is the kind of the average of the covariance of these xj's from j from 1 to p at a pair of the latent points z and z prime, right? This defines a positive definite kernel. And by the RKHS reproducing kernel Hilbert space theory, we know that we have a kernel, we can define a feature map. So this maps the latent space into some reproducing kernel Hilbert space. And the image of that is what what the authors call the feature manifold curly M in the paper. And also we can relate that to the data manifold, right? We can look at how the xi's, x1 up to xp, the coordinate functions, they are evaluated for all the possible z in the latent space. And the paper essentially connects these three objects, the latent manifold, or the latent space, or the latent manifold, and then the feature manifold, all the way to the data manifold in a mathematically transparent way. So they move from the low-dimensional space to the infinite-dimensional Hilbert space here, and then back to the high-dimensional space. And through this link, we can see how the geometries of the latent space get transferred to the high-dimensional space Y here. And the first link from the latent space to the reproducing kernel Hilbert space is using the kind of RKHS theory. For example, if we assume that the kernel here is continuous and positive definite, then from RKHS theory, we know that the feature map is continuous and injective, and then we see that this curly M is homeomorphic to curly Z, and this is mentioned by the authors in the talk just now. And in some sense, this is not too surprising, because we start with a d-dimensional latent space. We expect to end with something that's d-dimensional intrinsically after we apply a feature map here. However, what's more interesting is that when this kernel F is actually when the kernel F is actually isotropic and stationary, so this is something that I think the author didn't really cover in the talk, but it's actually a very nice part of the paper. When F is isotropic and stationary, we can actually show that the feature manifold curly M is locally isometric to the space, the latent space curly Z that we start with. So we get more geometric similarities between Z and M. And also, there's another result in the paper saying that if the kernel is sufficiently smooth, then the eigenvalues of the covariance function is decaying sufficiently quickly, and then we can see that a lot of the variations can be summarized in a low-ranked part of the feature space Z. So this is the link between Z and M, and the second link between M and Y is provided by random projection theory. And this is another very nice part of the work. And the author showed essentially that, well, once we have moved from, sorry, this should be a Y here. Once we've moved from Z to the M, and then we can view the data. Well, if we ignore the noise part, the additive noise part, we can view the data as a random linear projection from the curly M space. Okay. And because we can view this as a random linear projection, this is conceptually similar to the Johnson-Lindenstrauss lemma from random projection, from the random projection lemma, the random projection theory. And when the number of coordinates is sufficiently big, and this is actually shown by the author in one of the visualization just now, we see that the space of the data Y is actually approximately isometric to the curly M. So the geometry is carried from the curly Z to the curly M and back to the curly Y, and all the way around. So this is all. Overall, I think the latent metric model is a beautifully constructed object mathematically. But as a statistician, I'm also interested in the question: why does this? What does this new model buy us, right? Why does this new model why is this new model important to practitioners? First, I think that this new model gives a unifying view that links the latent geometry, the kernel feature geometry, and also the data geometry in a very coherent way. But actually, I think what's even nicer here is that it allows us to explain why some common procedures work. So Patrick mentioned in the talk just now that the theory indicates that, well, maybe PCA itself is enough. And at the beginning of the talk, I remember we have some discussions about, well, t-SNE and UMAP are often used in practice, and their use is preceded by linear dimension reduction. These non-linear dimension reduction techniques are often preceded by linear dimension reduction techniques to a space of moderate dimension. And actually, I think this language of latent metric models is able to explain why this combination of linear followed by nonlinear is justified. Because if we think about the kernel being sufficiently smooth, then in the RKHS, we should be able to see most of the variations within a small number of coordinates. That's why PCA is justified. And once we've done the PCA, of course, we have reduced we've done some linear dimension reduction. The actual manifold is even lower dimensional, and it's not necessarily linear. And that's why it justifies the use of t-SNE and UMAP, because of the low intrinsic dimension of the manifold. So I think the theory is actually coherent with what people are actually doing in practice. And this is very nice in the sense that we have a new model and it's able to explain why common procedures work. And the paper has many interesting results, and I think that it can. So I'll start with some discussion points that I think it's and of course I think there are many people who will also contribute to the discussions later on. So to me, one of the interesting questions here is how do we interpret this latent metric model, right? Do we really interpret that as in a mechanistic way, or do we just view that as a mathematical model, as a convenient model to represent the reality? So the reason I'm asking this is, for example, in one of the central ingredients of the latent metric model is the set of random functions. If we think about these single-cell transcriptomics examples in the talk just now, do these random functions arise as some kind of in a mechanistic way because how people are measuring the gene expressions, or is it more as a kind of just a convenient way to view the space of the transcriptomics? So this is my first question here. Okay. And also, the theory, for example, the theory about the approximate isometry requires the kernel F to be isotropic and stationary. So, so I want to ask, like, how do we interpret this in practice, right? Does this, what does this imply for specific coordinate functions themselves? And as practitioners, how do we assess whether this is a realistic assumption in the particular example I'm dealing with, or I'm just wondering whether this is always true, because there's this latent space curly Z, right? Can we just stretch the latent space so that we flatten out this anisotropy, right? If we have any kernel that's anisotropic, we can always flatten this out by suitably reparametrizing the latent space curly Z. So this is always satisfied. Another direction of discussion is about the empirical relevance. So we have already seen that, at least the way I understand it, that latent metric model is able to explain why some of the existing workflows make sense. But what would be more interesting is if the latent metric model can influence our workflow in the future, right? So if they can affect the workflow of practitioners. For instance, whether the induced kernel geometry that we have learned from the latent metric model can be tested or should be tested before the practitioners carry on subsequent analysis. And does this model tell us, for example, how many principal components we should use before we carry out t-SNE or UMAP? In the two examples that the authors have presented, one of them has reduced the dimension to 6, the other has reduced dimension to 14. Is there some, how should I say, reason that this should be done, or how do we actually choose the dimension? And does the latent metric model tell us how we choose it? And this is another interesting question I think we can discuss. And in addition, we can talk about how we can generalize the model. So the current latent metric model we map from the curly Z space to the feature space using the phi map, right? And then we use a almost like random linear map to go from the feature space to the space of data. Is there any scope to develop a theory for nonlinear maps? Because this will be what people are actually doing in practice. These are related to the autoencoders and the generative models. And I think these are all possible directions for discussion. Finally, to conclude, I think the authors have done a great job connecting data analysis, kernel methods, and geometric learning. They show that manifold structures, which we often take for granted, can actually emerge naturally from random correlation structures in the data. It's I think it's a very technically rich and conceptually satisfying paper, and then one that will certainly stimulate further discussions. So I would like to thank the authors for this beautiful and thought-provoking contribution. Thank you.
Thank you very much for the vote of thanks. Now I would like to call on Eddie Amari from École Normale Supérieure Paris to second the vote of thanks. And
hello, everyone.
okay, he's here. Good.
Can you see my screen?
Yes.
Yes? All right.
Yes, perfect.
Wonderful. So, hello, everyone. So, I will start by congratulating the authors for this paper, which is, to me, a pretty interesting paper. This has been quite puzzling for me as someone who working deeply into the manifold hypothesis and differential geometry and statistics. Overall, just to mention, this is to me very amazing that more than 100 years later, after the invention of PCA, which you have the original picture from Pearson's original paper, quite amazing that we are still following this, finding new results on these. So as I said, this has been quite puzzling for me, and I will share a few interpretations, comments, and questions here. Starting from the very first definition that the authors presented very nicely. So you have this kind of structured data matrix in which your rows are going to be independent, your individuals are independent, which is pretty common, and your features are not going to be independent, but column will be implicitly independent conditionally on the latent variable. So it's pretty well explained in the manuscript that you have a kind of a dual way to see that. So a top-down consequence for this model is you can see your points yi's as just being random projections of the infinite dimensional feature phi of zi plus random noise. So here you have your phi of zi living in possibly infinite dimension, of which you just observe random slices in dimension p, and those random slices essentially are projections in the sense that this matrix, which goes from the RKHS to the ambient dimension p, is on average an orthogonal projection here. So you have this structure showing up, and here I would just like to try and reframe what my manifold hypothesis is as a differential geometry in this field. Is say, for simplicity, that your latent space is a unit ball in small dimension d. Then if you stack your features x1 through xp, well, we usually, discarding the noise sigma, assume that our x is just deterministic and smooth. So this is the kind of assumption that we do. And so here, this is a very classical single patch manifold assumption for theoretical purposes. And low intrinsic dimension for this object, this x of z, is going to be assuming that the Jacobian of my matrix, the Jacobian, sorry, of my embedding is going to be low rank. Okay, so here we're talking about a low intrinsic dimension. So this is to be compared to what we're talking about today. For instance, say x is just pure noise, meaning that everything is centered. So here again, z is fixed, but x is random now. Here, what we are assuming in the present work is the low rank of some covariance operator, which is here saying that some extrinsic dimension of data is small. And when we frame this in this way, an interesting question that I would like to discuss, in fact, would be the link between the two or any intermediate concept. Okay, so here you have something which is very differential. Okay, so this is for sake of technicalities, of course, but which is inherently not average. And here we have something which is completely average and not differential at all. And I will come back to this for maybe finding an intermediate concept. And this really has maybe to me implications in trying to denoise intrinsically manifolds as such. Probably most puzzling for me was this randomness and stationarity of the xj's. I think the authors made a very good job at giving examples in the manuscript and in their talk today. In the article, maybe the most compelling example they gave to me was the time series example, in which they were considering temperatures in different cities on Earth and recovering the intrinsic geometry of essentially of Earth. All right, so this also maybe has implications for random features, which are very commonly used if you're doing supervised learning. But I'm really wondering what's the actual extent to what kind of data we would be able to push this kind of stationarity and remaining in low rank. All right, so we have this idea of for a given zi, which we obviously don't observe, we have these repeated measurements x1 through xp, repeated measurements because the rank of this covariance operator is small, but obviously here somehow independent. I was just I just wanted to mention that there is a recent line of research which tend to say that at least experimentally, token embeddings do not fulfill the manifold hypothesis. This would be very interesting to study what this particular framework. As for maybe the main result of the article, I'm just restating what the author just presented. Somehow we can view these results as a kernel PCA with an unknown kernel, right? We do not know the kernel that we're looking at. And here the high dimensional P is going to help us somehow estimating the kernel. And therefore we have this quite exotic regime in which n grows large and P over n grows large together. So there must be probably links with kernel PCA, at least for studying a term which is independent of P. Here, a question, geometrically speaking, is the question of what are we looking at in high dimensions? So you have extracted a very specific feature that PCA is recovering the features here. But here the features actually depend on the ambient dimension, because everything depends on the kernel, which itself is indexed by P. And there is the question of the stabilization of this geometry and what actually data looks like in this very high dimensional, infinite dimensional space. And again, this has been mentioned earlier, really a major extension from a mathematical point of view would be what happens for infinite rank. So if you track the constants in the proofs, this is the formula that you end up getting. Okay, more like an opinion than a question. I think that this bibliography on kernel PCA from maybe the 2000s might be helpful. About the geometry itself of the processes that we are considering today, there's actually a line of research from 2015 to 2016 that comes from Adler, Krishnan, Taylor, and Weinberger, who actually considered random Gaussian processes, x1 through xp, defined on some intrinsic small dimensional manifold, so which we would call Z here. And what they show is that after projection onto the sphere, which is probably purely technical, the regularity of the embedded space, which is the reach, I do not have the time to detail very much on this, actually stabilizes towards something depending on the covariance structure of the underlying Gaussian process. And the reason why I'm considering this and presenting this today is they happen to have something depending on the variance of something, of a variance, sorry, conditional to both the points next to xz and its differential. So it looks like there is a structure in between the covariance kernel and the Jacobian that I was mentioning earlier. Finally, I will more like ask a question about very complex data structures, especially for image data, in which this stationarity is not very clear to me, where data has been empirically shown to lie on some manifold, perhaps, but more likely would lie on the union of manifolds with different dimensions, for instance. So here I'm showing a plot from Brown and al. Called Testing the Manifold Hypothesis, in which they have box plots of dimensions for, say, ImageNet, in which they computed dimensions for each class in ImageNet, which is a data set of different simple objects. So I would be very happy to see the latent metric models capture this kind of data. All right, I have to complete. So again, this is a very good point of view for dimension reduction. The theoretical foundation of PCA and then data analysis methodology is, to me, amazing. And also from a purely theoretical point of view, this idea of seeing the manifold hypothesis as just another high-dimensional phenomena is quite fascinating. So I will end with by congratulating the authors again and seconding the vote of thanks.
Thank you, Eddie, for your presentation. Now, I'm sorry. I would like to thank all the presenters for their insightful presentation. And according to tradition, I would like to mark this discussion with a round of applause, which unfortunately is online, but I hope the authors can feel our appreciation. So now I will move on and open the discussion. I mean, some discussants have already registered, and I would really appreciate if they could keep their intervention to 3.5 minutes. And as I said, we start with those who have already given their name. And if somebody else would like to comment or intervene, please just write in the chat. So the first discussant is Carrie Pribb from Johns Hopkins University, which hopefully she is online. Yes, he's online.
Good. So you can hear me and see the screen? Is that true? Yep. Oh, okay. So it's my pleasure to participate this afternoon. As is my wont, I shall proceed narrowly, focused, and passionately, but out of character, but by necessity, I'll keep my comments short. The punchline is that Nick, Annie, and Patrick have produced a piece of work that really matters to me. So my remaining 200 seconds, I want to just go through this list of why this matters to me and why I think that this paper reinvigorates a research program that we've been playing with for quite a long time. So back many years ago, Ed Scheinerman, a graph theorist at Johns Hopkins, where I am, talked incessantly about what he called random dot product graphs. And the idea is that I have a graph on n vertices and the randomness is in the edges. And there is a matrix X, which I think of as n by d. So n rows, each is d dimensions. And such that the inner products are in the interval 0, 1. And so the matrix P, which is XX transpose, would be n by n. All the entries can be interpreted as probabilities, and those are the connection probabilities for a random graph. And Ed has a whole series, Ed and collaborators has a whole series of papers. Now, he's a graph theorist, so he cared about things like small world properties and whatnot. Then In 2002, Peter Hoff, Adrian Raftery, and Mark Hancock came out with this JASA paper on latent space approaches. And that really got me excited from a statistical point of view. And so what we have now is a d-dimensional random dot product graph, and what we call the adjacency spectral embedding that Patrick mentioned is the truncated eigen decomposition of the adjacency matrix, and that's to be distinguished between the Laplacian spectral embedding that was all the rage back then. And so what we think of is we have this parameter matrix, if you will, the n by dx, and when you do this adjacency spectral embedding, you get an x hat, which are the scaled eigenvectors. And so Daniel Sussman's paper in JASA 2012 showed that the rows of this truncated spectral decomposition of the adjacency matrix converge to the true capital X, the rows of the true latent position matrix, up to an orthogonal non-identifiability, of course. And so that's why we're able to put the hat on the X. It's a proper statistical estimate of the latent positions. Then Avantia Threya and colleagues showed that the rows of this estimated matrix capital X hat have central limit theorem associated with them. That is, there's an asymptotic normality associated with this spectral decomposition. And then Joshua Cape and colleagues showed that in the 2 to infinity norm, we get this uniform convergence of X hat to X. And so now we have lots of tools to study this adjacency matrix, adjacency spectral embedding. Going back a little bit, though, Min Tang and colleagues in 2013 in the Annals of Statistics talked about taking a latent position model, not necessarily a random dot product graph, where we have unknown kernel, and doing the adjacency spectral embedding to a dimension p, where p grows with n, goes to infinity. So in this case, Min was able to prove some universal consistency properties of this situation. But now we're in p dimensions even instead of d dimensions. Well, Madeline and Alex talked about big matrices being approximately low rank. So that reinvigorated the understanding of Min's paper. So in 2020, Patrick published the Manifold Structure NeurIPS paper, and that really excited me because the idea was that interpreting Madeline's real data are low rank as it's a low dimensional random dot product graph, but living in a high dimensional intrinsic space. So if we go back to Min's 2013 paper, we did not take advantage of a low dimensional manifold structure. But now with Patrick's 2020 work and this new work by Nick, Annie, and Patrick, there's this low dimensional manifold that we can take advantage of to do statistical inference. And so Michael Trossett and our team talked about taking this, learning the one-dimensional submanifold when I'm doing inference on random dot product graphs. In that paper, that's motivated by the Nick, Annie, Patrick kinds of results. The idea there is that we're first doing this high dimensional ambient space embedding and then using the random dot product graph concentration results. But the new paper suggests that we might be able to do this directly. So just in closing, I'd like to say that I've already talked to the authors. I want Riemannian structure on the manifold, but they'll give me that eventually, I suppose. And I want to understand how to exploit the low dimensional manifold structure directly rather than just after this adjacency spectral embedding into ambient space. And so with that, I'd like to thank the authors and try to stop sharing.
Thank you very much. Now I would like to call on Joshua Cape from University of Wisconsin-Madison.
Hi, everyone. I don't have a slide to share, so I'll just speak briefly. I want to congratulate the authors, obviously, on a very fine piece of work. The focus on first principles and generality to me is a particularly salient feature of this, enabling a flexible workflow, bringing together concepts from classical multivariate analysis, as well as what can be described as modern topics in statistical machine learning. I think this paper provides something for everyone. Theoreticians and applied data scientists alike stand to benefit by studying it. On the theoretical side, the high probability row-wise uniform error bound in theorem 1 is a notable contribution that won't surprise people who know my interests. Sort of loosely speaking, theorem 1 establishes that the entire PCA embedding, viewable as a point cloud in low dimensional Euclidean space, learns implicit manifold structure in the latent metric model. It should be noted that theorem 1 achieves a more fine-grained error control than, say, if you were to merely pursue an operator norm bound or a Frobenius norm bound. So as Patrick and the authors have highlighted in the talk and throughout the paper, really there are two key overarching ingredients in the proof approach there. The first being deterministic matrix perturbation analysis. The second being the use of probabilistic concentration inequalities. The latter is by now rather mainstream in modern statistics, given the wide availability of numerous textbook length treatments. Roman Vershinin's book, Joel Tropp's book, Martin Wainwright's book all come to mind. The former, on the other hand, namely sort of fine-grained deterministic matrix perturbation analysis, is a little bit more modern, though, and perhaps less well known, but has received a lot of attention in recent years. Patrick gives credit to the Lazinski et al. 2016 paper for some of the decomposition techniques used here. There, originally for the purpose of latent position estimation in random dot product graphs. For context, though, that 2016 paper, it does extend and build on earlier preliminary developments in Lazinski et al. 2014. That's an EJS paper focused on stochastic block model. The existing literature on RDPGs has expanded, and so there's considerable maturity in this space now, both for graph data and outside of graph data. Spectral methods in data science have emerged in recent years, really as a large area of vast interest. There's now a very nice monograph on that, Chen et al. 2021, providing a nice entry point for people in this. There's been some discussion of the finite rank assumption 6 needed for theorem 1. So recent work led by Min Tang provides fine-grained perturbation analysis in the context of infinite rank kernels and general eigenvalue decay. I saw that Patrick generously cited that work, and I would say that it suggests a path forward for exploring the absence of finite rank. In theorem 1, a random orthogonal matrix appears, and that might to some be unfamiliar or unexpected. It should be emphasized, though, that this quantity is required in general and can't be readily dispensed with. There are similar considerations regarding the alignment of embeddings and the orientation of latent position estimates appearing for indefinite orthogonal matrices in a paper by Patrick, also in JRSSB 2022, as well as for signed permutation matrices in a 2022 paper by Carl Rowe and Butze Zhang, also a JRSSB discussion paper. But in addition to that, the random orthogonal matrix in theorem 1 is not arbitrary in the sense that if you study the proof and see where it comes from, it is structured. It arises as a product of other random orthogonal matrices appearing at various stages of the proof. And in some simulation settings, it can be numerically computed. So maybe last but not least, regarding pedagogy, in my view, this paper stands ready to vivify the present day undergraduate and graduate curriculum on multivariate analysis and statistical machine learning. So with that, I want to thank the authors for a lovely paper.
Thank you very much. And I would like to call Masaki Imatsumi from University of Tokyo.
Yeah, thank you. Sorry, I'm now turning on. Oh, yeah, it works. Yeah. So yes. Yeah, maybe it works. You can see the screen. It's okay. Yeah. Thank you for the introduction. Then, first I'd like to say that congratulations, the authors for the great paper on this book, and I'm very glad to be here. So I'm really happy to give my thought on this paper on the statistical explanation of the manifold hypothesis. And I'm Masaki Majin from the University of Tokyo and Riken from Japan. So yeah, and I personally very interested in kind of this topic, data with intrinsic dimensional structure. And as we know, very modern science are very I mean, we can frequently see the kind of the data with nominally high dimensional, but the intrinsically low dimensional, including the very famous distributed data, nominally 3-dimensional, the intrinsically 2-dimensional, and also if we consider data images, MNIST datasets, very famous one, with a nominally over 700 dimensional, but intrinsically 30 dimension. It means that in the high space, we can observe the a low dimensional set, which include meaningful images as the letters. And yeah, it's very common phenomena if we observe in many data sets. And yeah, we are very we know much we know that the modern day many data science technology include statistics and machine learning very actively utilize this structure. Something that is explicit and something implicit. Yeah, and we fully utilize this structure. So and based on the situation, this paper proposed latent metric model LMM, so which represents the data structure by a fully statistical model. It means that in my understanding, so I consider this a data point. We can observe the data points, then after consider some of the random functions whose domains is the latent space. Then we can regard kind of the data points can be regarded as kind of output of the random functions of the samples, some sample points in the latent space. So, and if we have the random functions, we can define a covariance function of the random functions. Then we can extract a feature map from this covariance function. Then we can achieve a very nice model by using the feature map that is formed that observe the data points can be output of the kind of the feature map plus some noise. Then also a range of the feature map can define a manifold structure on the naturally defined manifold structure from the data distributions. So it's kind of a very nice a general framework by using the feature map from the statistical aspects of the data. So, and my feelings that is kind of a really nice approach, a very unified and fully statistical driving approach. And we do not have to use kind of domain specific knowledge, but only we use kind of the simple statistical model, and then we can fully define many nice properties. Then we can handle the really a general, a broad class of the low dimensional manifolds with kind of the minimal mathematical procedure, not so complicated. From the natural derivation, we can enjoy the nice properties, and then we can enjoy the many clear connection of the geometric property between the latent space and the data spaces is a very nice point. So yeah, I really enjoyed this paper. And based on the paper, my personal interest is that the kind of possibility of the extension for the more real, complicated situations. So as we know, there are many modern complex data has the really we can observe the many more and more complicated data structure, and to handle this data effectively, we have to develop the more simple but flexible and non-regular mathematical characteristics that are pretty important to handle this kind of modern data, I believe. So, and for example, so I'm interested in kind of the non-regular cases of the data distributions. For example, if we have the covariance structure, or to describe the data distributions have a singularity, covariance functions discontinuous something, kind of some. It's kind of a special situation, but it can appear in the real situation. And also another interesting cases heterogeneity of the local dimension, the dimension of the data low dimension structure is not uniform. It means that the data distribution is a mixture of the low dimensional parts and a medium dimensional part. And in order to handle these cases, we need some more flexible and more fruitful mathematical tool or model to study this situation. So, and then I know that I have worked on like a neural network studies, and I sometimes show that like deep learning can adapt to the situation. And also, I'm expecting that like a LM framework can adapt to these kinds of non-regular cases very effectively. And I hope that LMMS may offer the more like a flexible and also rigorous mathematical analysis to adapt to the situations and enable that to handle the many like complicated modern data structures. Okay, that's all of my talk, and thank you very much for the nice work, and thank you much for listening.
Thank you very much. Now I would like to call on Michael Trosset from Indiana University.
Sorry, I'm trying to stop my screen sharing, so I mean, but I haven't found out how to stop my share. Yeah, is it possible to stop my sharing? Sorry, it's okay.
I think it's just the arrow up that you have to click on.
Yes,
it should be on the right of your screen.
Yeah, I think so. So sorry about that, but I have not found sorry. Okay, I personally I mean look at this meeting and join again. So yeah, thank you.
Okay. So now we have Michael Trosset.
Well, I'm having trouble sharing, so I will dispense with my one slide unless Judith wants to put up the file that I sent her. In any case, greetings from Indiana. I too commend the authors on an elegant, thought-provoking paper. In my brief remarks, I'd like to comment on the tension between using the word manifold to describe an arbitrary latent domain on the one hand, and to describe formal mathematical structure on the other. The present work originated in a 2020 conference proceedings paper that showed that latent position graphs could be understood as random dot product graphs with latent position vectors in a set of low Hausdorff dimension. As previously mentioned, Carrie Prieb and I found that result tremendously exciting, as we had just begun studying random dot product graphs with latent position vectors on low dimensional Riemannian manifolds. And that formulation allowed us to develop methods that learn manifold structure for the benefit of subsequent statistical inference, and also to prove theorems about the performance of those methods. But we wondered, how realistic is our formulation for modeling actual data? Hence, we saw Patrick Rubin Delancey's 2020 result as providing additional motivation for our research, and we now quote his result frequently. But we still wonder, might we be using Riemannian manifolds to model low-dimensional sets that in no way resemble actual manifolds? Now, in my view, the latent metric space model for measurement data provides an elegant way to construct generative models that satisfy the manifold hypothesis. If one constructs a nice latent domain with a certain topological or metric structure, then one observes data with the same structure. But suppose that one wishes to understand the structure of data produced by an a priori model. Recall, the 2020 paper investigated the behavior of the already well-established latent position model for random graphs. So I ask, how does one reformulate an existing model as an LMS? And how does one then determine the properties of the latent domain induced by that reformulation? In particular, how does one decide whether or not an existing model satisfies the manifold hypothesis? Much remains to be done, and I look forward to future developments. Thank you.
Thank you very much. Now I would like to call on Wanye Wang from National University of Singapore.
Hi. Let me try to share my sorry. Sorry, I have some problem sharing, but I have sent the slides to Judy, so maybe can you share like at your end?
Judith or Anna, do you think you can share?
Yes, give me 1 second. I'll get the slide pulled
Okay,
up.
thank you very much.
Thank you very much. Yeah, so maybe I just like start talking. So hi everyone, I'm Wan Jie from National University of Singapore. First of all, I want to congratulate all the authors for such a wonderful work. I mean, like for PCA, we know that people usually use PCA as a pre-processing step. And that's also like one reason that many statisticians try to set up the theory in this, like about the PCA on how good it is and this kind of things. So like the bound, like the 2 to infinity norm bound and this kind of things. But for this work, so under the latent metric model, the LMM, the manifold hypothesis, so like very flexible framework, the authors has set up the relationship of the PCA, like the performance of PCA, which connects the underlying manifold and also the feature map. So I want to start with like the like a reminder of the notations in this paper. So where Z is for the underlying manifold, and this M is the manifold for the feature map. So Judith can click one. So in this paper, so the authors had set up like the two propositions where if it is like distinguishable, then there will be homomorphism between the Z and M, so the underlying manifold and the feature map. And if like the stationary holds, then there will be isometry. So Judith can click. Thank you. So I want to connect it to one of our recent work, which is under review, where we really use PCA plus Laplacian eigenmap on the manifold data. So it can be treated as a special case of this work, where in this special case, our underlying hypothesis is that the underlying manifold is 0, 1, which is very simple. The geometric distance is just the distance between Z1 and Z2. So we use PCA to find the feature map, like here we call it feature map, and then we have some assumptions on this feature map between this feature map and the underlying manifold Z. And under this assumption, we can use the Laplacian eigenmap to recover the Zi. So where Zi can be treated as, for example, the angle of the car images. So here I have a question. So actually in our assumption, we will require the relationship between M and Z as that there is no folding, but there can be some bounded distortion. So it's not the exact isometry in the current paper. So but like we still need some kind of isometry here. So Judith can click. Thank you. So therefore, I have a question like for the authors. I wonder if there can be some discussions on the requirement of FZ1, Z2, so that the feature map, the approximated feature map, can achieve such kind of a no folding bounded distortion condition. Yeah. So so that's my question. Thank you.
Thank you very much. And now I would like to invite Gazina Reinert from University of Oxford.
Thank you. the screen. Okay, can you see my screen? Okay, can you see my
Not
screen?
yet. Yes, now yes,
Okay.
it's fine.
Good. Okay, so first of all, this is very impressive work. So we have our noisy data, and then we have a PCA embedding, and from that we might carry out a nearest neighbor graph construction, and then analyze the nearest neighbor graphs, because the shortest path in either of these graphs give information on the topology of a hidden manifold associated with the data. And it's a very convincing workflow. So I'm coming from the area of networks. So a bit like Carey and like Michael Trossett, I'm thinking of latent space models. Hoff was already mentioned. So here the data are not real valued Euclidean data, but binary edge indicators, but have possible covariates. Then they're embedded in a latent space, usually some Euclidean space, usually often via some distance between pairs of vertices, which arise from some observations possibly. Then a network model is constructed with independent edges conditional on the latent variables, and the random dot product graph are examples of this. So the edge probabilities then depend on covariates and distance of positions in a latent space. So like my predecessors and like Nick saying, we want to possibly revise Gaussian process latent variables. I wonder whether it's time to revise these latent space models in view of the new results. So main question is, can the paper shed new light on latent space models? So I was thinking, for example, if we start from an adjacency matrix and then we use the embedding workflow, which we have, how would that model perform? So what kind of geometry would we find if we just do the k-nearest neighbor construction? Or if we start from noisy data and use the embedding not for the k-nearest neighbor graph, but we could also use the embedding to build a random dot product graph or some other latent graph. Could realizations from this network model provide perhaps additional information about the manifold? Because the k-nearest neighbor graphs and graphs with independent edges behaves quite differently, for example, in terms of clustering. So these are my questions. Thank you.
Thank you very much. Now I would like to call on Alexander Model from Imperial College London.
Hello. Can you see my screen?
Yes. Yes,
okay,
thank you.
Great. Okay, well, I'll start by saying I think this is a massive accomplishment. I know this has been 5-6 more years of work, and it's a really comprehensive and enlightening explanation about why the manifold structure might arise in data. And I just wanted to, in this discussion, draw some connections with the literature on mechanistic interpretability of large language models. So there's been recently a lot of excitement and interest in manifolds which emerge in embeddings and activations and representations generally of concepts in large language models. So Nick, Patrick, and I have done some work on this recently, and this is a picture from a recent preprint where we've looked at some embeddings and internal activations from some large language models, which are perhaps 1,000-dimensional, done PCA into 3 dimensions to visualize them, and we see that there is interesting manifold structure that arises. So I wanted to, in this discussion, draw a connection between the work on the latent metric model and on neural networks. So basically, I've done some derivations and can show that if we have an input space Z, which is on a sphere, and we put that through an MLP, then at initialization, so if the weights of the neural network are Gaussian with appropriate variances, then this MLP is a latent metric model. And not only is it a latent metric model, if we derive its mean correlation kernel, that kernel is a function of the inner product between the latent variables. And this implies that the feature maps associated with these are isomorphic up to scale, according to the theorems in the paper. So this expression for the mean correlation kernel for popular activations like the GELU, which is the state of the art, and sigmoid activations, we can get explicit elementary expressions for this mean correlation kernel. We can also show that if the activation function sigma is n times differentiable, then so is G, so the results hold. And the GELU activation, which is the state of the art, is analytic, so infinitely differentiable. So this holds. As I mentioned, yeah, the theorem proposition 4 in the paper suggests that this means these feature maps will be isomorphisms. And finally, again, if the activation functions are analytic, then the kernel will be smooth. And there's some papers showing that in this case, this means that the kernel has geometric eigenvalue decay. So basically, in short, it's almost low rank. So we could hope that some of the ideas from the paper will transfer into this case. So in conclusion, I hope that this work will kind of get people in statistics interested in looking at mechanistic interpretability of language models and understanding the geometry that emerges inside language models, and trying to use this to help us understand how language models and AI models more generally work under the hood. So thank you.
Thank you very much, and I would like to invite In-Ki He from University of Wisconsin-Madison.
Thank you. I think I may not be able to share. Can Anna help share it, my slides?
Yes, I'll get those up right now.
Thank you. So first I will start to talk. I want to congratulate the authors on such a seminal work and inspiring discussion linking this manifold latent structure and PCA in a general setting. And I find it particularly of interest to me that in the data example and the simulation example, the authors demonstrate that the shortest path in the PCA space, large ambient space, could have linear relationship with linking the shortest path in the latent space Z. Say in this torus example, they have demonstrated in the simulation study. However, when we estimate latent embeddings in practice, oftentimes we want to build the interpretation with observed covariate. That gives me a question that in practice, we don't want to manually sort or search over all the possible embeddings and trying to get interpretation. Instead, it will be better if we can have some data-driven procedure to link the potential manifold we learned and observe the covariates for a data-driven interpretation, and which can be particularly useful when the data set gets larger and larger. Inspired by this simulation example by the authors, I was thinking that if we have some information in the latent manifold, can we build links between this PCA distance in the PCA space and the latent space? Next slide, please. Yeah, thank you. And for this particular latent embedding, they built the model with the Euclidean distance in three-dimensional latent torus space and the PCA distance. However, we know the intrinsic space in this example are two-dimensional. First is an angle or azimuth about the original θ1 for each observation, and another is another angle of elevation about the center of the tube, θ2. In practice, we may have some information, say, now we assume θ1 is known, and can we build connection between my θ1 angle to my latent PCA representations. Next slide, please. In this visualization, the authors show that these first 3 dimensions show a very nice kind of distorted structure over this torus with relationship over these 2 angles in their paper. So this inspires me that if we look at the shortest path in this M space now containing the first 3 dimensions of phi CA, I estimate by PCA, can we build the link between either this θ1 or θ2? The middle graph shows the shortest path in this 3-dimensional PCA space against the shortest path in θ1 space. Now, this shortest path representing the minimum angle between 2 angles distance. And to some extent, surprisingly, this does not directly follow their assumed model. However, we still see some kind of linear relationship on these 2 angles. On the other hand, if we look at θ2, now this relationship becomes quite noisy, meaning that we don't have very much meaningful relationship. Why would that happen? My interpretation is that if we look at this PCA phi space, this largest variation is dominated by this θ1 in the left top figure, as we can see. On the other hand, this secondary dimension, θ2, is characterizing the width of the bands, and that is kind of masked by the largest variation in the PCA space. So in summary, I think if we have some variation difference in the covariance that we observe, it is possible through this PCA dimension to recover its relationship with the most dominating largest variation, kind of utilizing this shortest path approach the authors demonstrated. However, it also shows that it could be difficult to build the link clearly on the secondary variation, say in θ2 in this case. Can we kind of build a model? In practice, if θ1 is already known, can we remove that variation from our model so that the secondary variation from θ2 would be more obvious and for interpretation without loss of information? That concludes my question here, and thank you very much. Yeah.
Thank you very much. Now I would like to invite Jan Botan from Imperial College London.
Yeah. Hello. Just let me share my screen real quick. Can everyone see it? Just a thumbs up or something?
Yeah, it's all
okay,
good.
Very good. Very good. I've seen this talk actually, I think 3 times, but it gets better every single time. So congratulations. But actually, this is the first time I've seen all 3 authors present, which is kind of very fun as well. Okay, so let's delve into it. So I think my main, question is somehow what is the statistical evidence for the LMM, right? For me, the manifold hypothesis is almost like a phenomenon that occurs in nature, right? We observe it, we think it happens, and we like to explain it. Of course, to do so, we must think of it like physicists in some sense. So we posit a theory. In this case, the theory is the latent metric model. We believe this is what's causing it probabilistically to generate these latent structures. But of course, to do in a sense, a very scientific approach, we need to validate these assumptions, right? And that requires multiple things. For example, for a given data set, if I tell you this is a data set, can you actually somehow tell me, oh, can be generated from LMN with a certain probability? Can I say probabilistically this is a good enough approximation, right? Although the authors obviously said this is a descriptive model, it's not meant to be prescriptive, but still it's good to see where description will lead to what we observe, right? Of course, there are theorems for behaviors of metrics on these quantities. I'm not sure how they would be used to construct such a, let's say, p-value or evidence. I haven't really thought enough about that, but I guess in one way to use the concentration inequalities, which is in theorem 4, for example, to build up some measure evidence, that's quite difficult because there is the matrix Q in there as well, right? And secondly, just to add on this point, I think that the authors do a very good job of convincing me that the LLM explains things that happens, the cell data set and so on. But I'll actually be almost reassured if it was unable to explain something, right? Because if something can explain, if a theory explains everything, then somehow that seems too broad, right? We need kind of more specific. We need to have something where it cannot explain, and that'll kind of make me feel better that it's not overly broad, right? So this is the main general comment. The following two comments are more kind of technical concerns. This second point is more I think partially my own failure to understand all the math behind it. Of course, I can follow the inequalities and so on. I can see everything that's happening from a like step-by-step point of view. But from a general global perspective, I'm actually not sure if theorem 1 is a consequence of the fact that most vectors of high dimensions, even random ones, would be orthogonal, right? A blessing of dimensionality in this case. Because obviously P over N goes to infinity, so somehow to me that makes it that things are more likely orthogonal than not. But I'm not sure that's the case. This is a true question. I didn't have enough time to go over the proof more carefully to understand this. And of course, secondly, the size of the ambient dimension R, we've seen many discussions on that already, so I won't bore you too much with my comments. But of course, like you make dimension grow of n at some controlled rate. We discussed that already. I think Eddie used the fact that you can put R into the bounds in theorem 1. Of course, you can slot R into theorem 4 as well in the same way that he did, I think, more or less. You get better rates, obviously, with more moments. For context, theorem 4 assumes more moments exist in the problem. And of course, like if you are in infinity, what happens? And obviously, I think Joshua gave some comment on that as well. And that could be a good, interesting direction of study. But I think my main point is somehow we need to have a measure of evidence for this. We need to be a falsifiable model in some sense. Right? That will convince me this is more useful to explain things that we see in real life. Okay, thank you very much.
Thank you very much. And now I would like to invite Joshua Achterberg from University of Illinois Urbana-Champaign.
Would you mind? Oh, wait, hang on, I found it. There we go. Oops. Okay, can everybody see my screen?
Yes.
Cool. Great. Yeah, so I just wanted to highlight some connections to subspace perturbation theory. If you know my interests, then this should probably come as no surprise. But I just wanted to congratulate the authors as well. I think it's a really wonderful paper. But I've done a little bit of work on subspace perturbation theory, so I sort of thought it'd be nice to connect the two. All right, so of course, this is their model. I don't really need to go into the details about this. This is verbatim the same notation that I believe Nick presented. But the key assumption here is that the kernel F is rank R, and it's got smallest non-zero eigenvalue lambda R F. Okay, and so this eigenvalue plays a key role implicitly. Okay, so this is their model, right here. And so kind of from the proofs, they show, roughly speaking, that XX transpose behaves something like P times phi transpose, right? And in the signal plus noise model, which is a common model used for studying subspace perturbation theory, we just have a low rank matrix plus noise. So when the kernel is low rank, we would expect that these two models kind of coincide. And so for simplicity, I'm going to be assuming that the noise is IID Gaussian noise. Okay, so the main question I want to sort of try to start to answer is how can we relate the assumptions about the latent metric model to the prior works on the signal plus noise model? Okay, so if you the theorem 1 requires that this kind of signal to noise ratio remains bounded implicitly. I read it as a ratio just for simplicity. And if you go into their appendices and you kind of hunt around a little bit, it actually requires a weaker requirement, which is that this signal to noise ratio is larger than 1 over n. And in the signal plus noise model, it's been shown that for a different signal quantity, which is lambda r of the low rank matrix, this ratio has to be larger than the square root of p times n when p is much larger than n. And that's sort of necessary and sufficient in a minimax sense. Okay, so the question now is whether this assumption here that's implicit in their proofs is necessary. And also shown in the appendices, you have to dig around again a little bit to find this. But I mean, it's quite technical and the authors do a really nice job of explaining it, but I did the digging. And so this is what I found is that lambda r of s, roughly speaking, looks like n times p times lambda r f. So after sort of some work, you realize that their assumption is that you have this signal to noise ratio requirement, which is 1 over n, And then in the signal plus noise model, you have this slightly weaker requirement, particularly when P is much larger than N, right? So this is going to generally be a weaker requirement. And so my conjecture that I'd like to raise is that theorem 1 continues to hold, albeit possibly with a worse rate than is presented in their theorem 1, but it continues to hold when this this weaker signal to noise ratio requirement holds. All right, that's all I have to say. Thank you.
Thank you very much to all the discussants. Judith, Anna, I don't think we have time for contribution from the floor, correct?
I think that's possibly right, and we'd like to give the opportunity to the authors if they would like to make any comment today before we close.
This is optional. It's up to the author. I would like to clarify.
Am I correct in thinking we close at 6 p.m. sharp UK time? 3 minutes.
Yes, we are due to close. Yeah, yes, at 6. You're right.
Okay, I mean, well, Patrick, Annie, of course, we haven't had the chance to confer, but you know, I mean, I think the first thing I want to say, and I'm sure Patrick and Annie would agree with me, is just to say thank you so much to everyone that's contributed something. I mean, literally in the amount of time that we've got right now, clearly we're not going to be able to get around everyone at all, but we really look forward to responding in writing, and that's part of the process to come, isn't it? I'm not sure. Patrick, Annie, what do you think? What should we try and do?
If we only have 2 minutes, I feel that if we started, we would only start picking some people and not others, and we'd feel we'd somehow been a bit unfair. So I don't know if it might be best to just thank you all so much for all your energies and your careful read, especially in this last comment, right, by Joshua of our paper. Annie, is there anything you're burning to?
No, I think that's a good idea.
Yeah, I think just with the time we have left, maybe it's not really a sensible undertaking to try to respond.
But,
that's perfectly fine. Anyway, you will have plenty of space in the written reply. So I would like to thank both of you, the three of you, sorry, Nick and Patrick, for such a wonderful contribution. Just to conclude, I would like to say that our next meeting is at the Ormond Conference Centre in London on the 22nd of October. It will feature the Series A paper, Balanced, Robust, Randomized Treatment Assignments, the finite selection model for the health insurance experiment and beyond. All details of upcoming discussion meeting can be found on the RSS website, and usually they are also announced to the members through newsletter and on social media. If you would like to receive an invitation to future discussion meeting, you can just email journal@rss.org.uk, and then you will be added to the discussant mailing list. And this is the end of this discussion meeting. I would like to thank everybody for coming along, not only the authors, also all the discussants, the proposer and the seconder of thanks, and hopefully I'll see you to the next discussion meeting. And for me, it's good night. Have a nice rest of the day. Judith, do you need to add anything, Anna?
No, that's perfect. Thank you so much, everyone.
Thank you. Bye-bye.